Hello viewers and welcome to this new STM32 tutorial video. As I usually forget this, but I'll try to remember today, please do like and subscribe. And I absolutely love it when you post some comments, post comments about the good and the bad, and that gives me more ideas of how to move on and how to create the next video. These are created pretty much as you see them, so please do that. In the last video, we created a sine wave on the digital analog converter and we were using DMA to feed that conversion. So we used the DMA transmit buffer to have the peripheral and the DMA do most of the work for us. All we had to do was calculate some sine values and put them into that buffer at the appropriate time. Today we will be looking at doing serial communication, serial receive with DMA. But if you have not yet looked at the last video, I suggest you take a look at that, because it will explain more in depth some of the concepts of the DMA. Now, normally if you would use UART to transmit, you would transmit from one MCU to another MCU, and you will have data going back and forth over that. Fortunately, for the sake of demonstrating and testing, we can actually do all this in one MCU. So what I have done is I have created, I made a photo of it here. I have created I'm using my standard STM32 world board, and I simply have a wire going from the transmit of one UART to the receive of another UART. So let's dive into the code for this. As usual, I have created a start project which I call STM32 world underscore UART1, and of course, as usual, I'll commit and push this to GitHub when I am done with it. I have also created our standard little code here where I am writing a tick to a serial port every second. So when running this code, at the moment, the output will look like this. It will simply call out a tick every second, and it will show how much time it had left in that main loop, which you can see over here. So that's about it. Now let's look at the configuration of the STM32 processor in STM32CubeMX. Now we are using a serial port over here to transmit data during but if you look down at the connectivity, there are plenty more UARTs we can use. So if we enable, say, this one, we will have the transmit here and the receive here, and I could use this one, but it doesn't matter. But I'll prefer to use this one because it will have the pins right next to it, and as a result of that, I simply have a wire running from the PA2 to PA0, and that is the setup I have here. So at the moment we can run both on 115,200 bits per second. We will see later that we can actually end up doing this much quicker. Now, when you receive, let's start to add some codes. So let's generate. I want to talk about this right away. Now, if you are receiving data on a UART, there are multiple ways you can do that. The basic one is you're pulling the UART. So you're pulling the UART and say, do you have any data for me? And if there is any data, then you process that data and move on. Unfortunately, that is obviously very, very inefficient because the processor will spend most of its time just checking if there's new data. You could also use an interrupt. So we could enable a global interrupt on this one, and then we could basically wait for a character. The interrupt will handle the receive. That way we don't have to wait for the data to come. We will be notified when there is data to be processed. Unfortunately, it will result in a lot of interrupts because you would get an interrupt for every single byte received on this, and that will create an enormous overhead. A much better approach is actually to use DMA. Now, in our QMX setting, we can add a UART 4 receive. So what we're going to do in this, we're going to transmit on UART 2, and then we're going to receive on UART 4. And we can have this DMA stream, which will transfer from the peripheral, the UART, to the memory. And as we did in the last one, we will use a circular buffer so that when the buffer is full, it will just start all over again. And we also get an interrupt halfway, exactly like we did before. So this is our basic setup. We'll keep the interrupt enabled, but we will also have an interrupt now for the DMA stream that is automatically enabled, and I don't think you can disable that. So we now have two UARTs. They're both configured to run at 115,200 bits per second, and we have a DMA receive buffer enabled. Receive a DMA receive stream would be more correct, I think, on UART 4 data stream. So we have a data stream there. So let's generate the code and let's start implementing some of these features. Now, as usual with DMA, it's a very good idea to have. We need a buffer, otherwise it makes very little sense. So let's define a buffer size. Define buffer size, and we could do a buffer of 64 byte. It is really not all that important. Then we need some variables, and we define them down here in our private variable. And what we need is we need a transmit buffer, which is a character buffer of that buffer size, and a receive buffer. That means we can transmit strings up to 64 byte because I'm using the same buffer size, and we have our DMA buffer defined, which is just basically a byte buffer. These are essentially the same, but it will result in a warning if you get them wrong. You can see we have our UART initialization code defined, and that's about it. But let's extend our main loop a bit down here. Where are we here? So what I want to do is I want to add here. I want to add a next TX next time we transmit, and we'll do that every second as well. And I want a transmit count, which we could set to 1 at the moment. So we can go down here in our main loop and say if now is greater than or equal to our next TX, then we do something and we increase our TX count, and we set our next TX equals now plus 1000. So how are we going to transmit? Well, we have our transmit buffer. So what I can do is I can use sprint F to print something into this transmit buffer. So I just print something rather long and add the TX count. So every second I'll get, and for our debugging purposes right now, I will print out this stuff on our console as well. So we are transmitting that transmit buffer, and then I can simply use a help function to transmit this buffer on UART2, and it is our transmit buffer, and I will typecast it here because this UART transmit expects, no, it should actually be okay. So anyway, it's and I will use the string length of the transmit buffer, so I will not transmit more than is actually printed into. In C, strings are terminated by a 0 byte. So basically this will add this to the buffer, but it will also add a 0 after the string. And that is, I want to transmit that 0, so that is why I say the length of the transmit buffer plus 1. Now, do notice that the hell UART transmit, since I'm not using interrupt and I'm not using DMA for this, is a blocking. So essentially, this will wait until this transmit is done. So let's try to build that and see if that builds. And it did. Let's try to run it and see what happens. You will notice before we were running almost 12 million loops. Now that has dropped to about 9 million loops, and we are transmitting this. This is of course because we are waiting for this UART transmit, and we are handling the strings and building the strings. So essentially now we are transmitting on UART2. We are transmitting every second. We are transmitting a string, and that string actually does change. So that is the transmit part done. Now let's move on to the receive part. Now I mentioned we were doing DMA, and initializing this is as simple as up here starting basically receive to idle. Now receive to idle is a feature I have not seen in anything but STM32, and it is really cool. Normally, if you're using DMA receive, you will wait for the buffer to be full. So if you set a buffer of 64 byte, it will wait until that 64 byte is full, or in case of a circular buffer, it will interrupt when it's half full and when it's full. And that is, of course, if we want to handle, if we don't know that we get data all the time, that is a bit, that's not what we want. Receive to idle is clever because it will receive into a DMA buffer a continuous stream of data, but the moment there's a pause in that data, I think if you miss 1 byte, then it will fire the interrupt and we can deal with it. So we read into this DMA buffer and we have the buffer size, and that is it. Now we are receiving data on UART4, but we need a couple of support functions to deal with this. And essentially there's some callbacks. As usual, if you go in and look at the code of the HEL library, you will see that there are some callbacks defined, and we need to override those callbacks. The first one is the RX receive event callback, and the other one we could put in here, I am going to cheat and copy the code I already have because I'm not going to do much there, is this. So basically if there's an error, we will get this one fired, and we just basically print it out and stop execution. Now the RX event callback is interesting because it is called with the UART as a parameter, but also an offset, and that offset will start is the offset in the DMA buffer. So what I'm implementing is something like this. I will copy here. because this RX event will actually be called more than when there's a pause. It'll also be called when the buffer is half full. But what happens there is that the offset will be the same. So I have to keep track of this offset. So in the beginning it's 0. First time it's called, it'll be something non-zero. I don't have that yet, so let's ignore that. So I'll check if the offset is different than the last offset, and then I will go down and I'll say if it is less than the last offset, then the last offset is 0, because it will roll around when the buffer is, remember it's a circular buffer, so it can go up to, in our case, 64, and then it will wrap around to 0, and we will keep track of this. Now, for each character that we are receiving, we will call a process character, and we will process the character in that buffer, and then we count up that last offset until receive. So we will need to implement our receive process character function. We can put it up here so we don't need to declare it. So we have process character, we receive a character, we have a string length that we keep track of our string lengths, and then we basically look at the character. If it is 0, we have received the entire string. That is the last character. But other than that, we will just add this character. Now, strn cat is a little bit dangerous because we could actually overflow our buffer, which is why we keep track of that strn length, so we don't end up receiving too many data. It will simply not allow that. So something like that should actually be working. Let's try to fire that up. Here we transmit and we are receiving exactly the same. That is it. That is all it takes. This one will now listen for strings. This is made for string. We could of course do binary data and handle it somewhere else, but as long as this string is 0 terminated and we transmit that 0, it will work. It will loop up. We could, just to see how that works, we could add a little more debug information. For example, we could up here in our receive callback, we could printf our offset the and of course we need to throw a new line on it. Let's see how that works. I mean, it'll be messy, but it should show us. So you can see it transmit, and then we get these offsets. And this string is so long that we actually get multiple of these calls between each, which is okay because it can be called multiple times. We know in this one, we don't know when the string is done. We just know that there is a break. It could be that we haven't received the entire string yet, and that is perfectly okay. So that is all it takes to add DMA to a UART receive. I had some extra code that just to illustrate, rather than actually printing this out, that looks messy, we could actually flash a LED. So let's try to do that. Now, I don't want to now this is operating so shortly that we wouldn't notice the LED flashing. We wouldn't be able to see it, but we can actually delay this a bit. So let's actually activate a timer just to show you how you can do a LED pulse. As usual, I'll do our 84 minus 1. So it's down to 1 megabit, and then here we can do 30,000 minus 1. Let's just, and let's have our timer interrupt enabled. Project generate code, and then what I want to do is I want to implement a function called, I actually have two functions, but I'll explain to them later. So we go up here and we add here. So basically we have a LED flash, which I want to call down here instead of this. And the LED flash, what it does, it toggles my LED pin on, low, but on, and then it starts a counter, and when that counter interrupt happens, I switch it off again. Let's try to run that. And it actually worked. I need to show you. So here you can see every time that interrupt is happening, it will pulse the LED for, I think it's 30 milliseconds it'll be on. But that's enough for us to see that it's actually pulsing. So that is pretty much, let me switch that off. That is all it takes to receive data on a UART with DMA. And as long as, I mean, this will work. It's important to know that this rather brilliant receive to idle DMA, it works even if there is no idle. If it just keeps pumping out data, it will still work, because what we're doing up in our code up here is that we are waiting for those zeros, right? We are waiting to receive a 0, and that is when we have received a full string. Now, the brilliant of this, I mean, of course we could probably have implemented this with a poll, but let's try to speed things up a bit. Now we're using 115,200 here, but we could use 2625 is the max, 2625 000, so 2.5 million bytes per second rather than 115,000. So let's shit, I did something bad there. Let's copy that, and let's do the same with UART 4. Parameter settings. There. Now it is running much faster than it did before, and there is no way we could keep up with this with interrupts. But if we try to execute this code, now running many times faster, 20 times faster than it did before, and you will see that it still works perfectly. It just interrupts quicker than more often than it did before, but the data is transmitted faster. So actually you will spend less time down in the main loop, because this transmit will be much quicker than it was before. I don't know, I didn't notice what the, can I see 9.8? It's not noticeable whether it's running faster than it was before. Anyway, UART DMA receive, that is all there is to it. As usual, thank you for watching. I hope a few of you survived to the end. If you did, and if you liked any of this, please like and subscribe. And until next time, if you have any request or anything you think I skipped over too easy, please add down in the comments, and I do read those comments, and it might very well mean that I change my next video as a result of it. Bye bye, have a wonderful day.